Good afternoon, dear friends. My name is Wu Yu, and I'm from Jiangsu University. Today, my topic is effect of the equivalence ratio on the propagation characteristics of hydrogen and air rotating detonation waves, considering a high frequency and small amplitude pressure inlet. I will start the topic of this report from the following four aspects: background, numerical method, results and discussion, and conclusions. The first part is the introduction of the research background. In recent years, detonation propulsion, especially rotating detonation engine (RDE), has received extensive attention. RDE is an engine propelled by detonation combustion and has many advantages, such as single ignition, small volume, large thrust, and high thermal efficiency. This slide shows the typical flow field structure in rotating detonation chamber (RDC) using gas fuel, including rotating detonation wave (RDW), contactor surface, oblique shock wave, and slip line. Among them, rotating detonation wave RDW propagates along the circumferential direction, and detonation products propagate along the axial direction. In terms of experiments, many scholars have studied the propagation characteristics of RDW by using different gaseous fuels such as hydrogen, methane, and ethylene under different import conditions, including the changes of inlet mass flow rate, equivalence ratio, inlet total temperature, and total pressure, and obtained a series of valuable conclusions. Last year, Bai et al. Studied the effect of equivalence ratio on the propagation characteristics of high-temperature hydrogen RDW. It was found that when the equivalence ratio was 1.32, the speed of RDW reached a maximum of 1,485.9 meters per second. In numerical simulation, a lot of research is also underway, including the study of physical conditions such as fuel mixing and inlet conditions, as well as the study of solution format and the development of new solver. Last year, Wang et al. Used the Avero centrifuge to conduct a two-dimensional simulation of the RDE of ammonia-hydrogen-air mixtures. It was found that with the increase of ammonia equivalence ratio, the detonation wave velocity decreased significantly and the NOx emissions increased. Next, the numerical method of this study will be introduced. The open source CFD software OpenVOM and the open source solver role-reacting centrifuge are used in the numerical study. The flux discrete scheme is Kognov-KMP. Euler implicit scheme is used to solve the reaction source term, and the second-order implicit Crank-Nicolson scheme is used for time integration. The size of the model is 200 mm long and 60 mm wide. The inlet is divided into 40 inlet units, and the area ratio of the inlet is 0.6. According to the previous research results, the diffusion term can be ignored in detonation combustion, so the compressible Euler equation is adopted in this simulation. Referring to our previous research results, under the premise of inlet pressure disturbance, 6 groups of numerical studies with different equivalence ratios were set up, and the equivalence ratio changed from 0.6 to 1.6. The amplitude of the disturbance is 0.1 MPa, and the frequency of the disturbance is 5 kHz. In order to verify the correctness and accuracy of the numerical format, the model with the same size was used. and the numerical solution was carried out with 3 sizes of grids under the conditions of total inlet pressure of 1 MPa and total temperature of 300 Kelvin. Finally, a similar flow field structure is obtained. We also sampled the pressure data at the same position, and the results are shown in the right figure. Because the focus of this study is not on the fine structure of detonation wave, the 0.2 mm structured grid is finally adopted. Next, the results will be shown. The left side shows the temperature and the pressure contours of RDW stably propagating under 6 cases, from which we can find that with the change of equivalence ratio, RDW changes from single wave to double waves and then to 3 waves. The detonation wave height is the largest when the equivalence ratio is 0.6. And when the equivalence ratio is 1.6, the 2 RDW heights are inconsistent. In our previous study of constant inlet total pressure, there were no 3 waves. By obtaining the evolution of pressure signals at monitoring points, we find that as the equivalence ratio increases, the RDW propagation frequency increases, and the high-frequency instability becomes obvious. Especially, the pressure signal is the most irregular when the equivalence ratio is 1.6. Furthermore, the peak pressure in multi-waves modes is higher than that in single-wave mode. Next, the equivalence ratio of 0.8 and 1.6 will be compared. Although they are both co-directional double-wave modes, the time required for them to form a relatively stable RDW is quite different. The RDW at the equivalence ratio of 1.6 is more unstable, and the height adjustment takes longer time. From the figures, we can see that until 3,000 microseconds, the RDW height is still inconsistent in the case of equivalence ratio 1.6. In order to quantitate the height changes of RDW, the height of RDW under 6 cases is counted. The left figure shows the variation of height within time, and the right figure shows the average height in the last 5 cycles of RDW propagation. From the 2 figures, we can find that the height of detonation wave oscillates approximately in the form of sine function, and the RDW oscillation amplitude is the smallest when the equivalence ratios are 1.0 and 1.2, within 1 millimeter. The average height of RDW at the equivalence ratio of 1.0 and 1.2 and 1.4 is not much different, but the amplitude at the equivalence ratio of 1.4 is more than 1 millimeter. With the increase of equivalence ratio, the average height of RDW decreases first and then increases. The third part is the statistics of RDW wave velocity and velocity deficit. As the equivalence ratio increases, the propagation velocity of RDW increases first and then decreases. And the propagation velocity is the largest when the equivalence ratio is 1.2. On the contrary, the velocity deficit increases with the increase of the equivalence ratio and becomes more obvious when the equivalence ratio exceeds 1.2. Finally, we evaluate the propulsion performance of RDE. This figure shows the average thrust and the field-based specific impulse at different equivalence ratios. From the figure, we can find that the maximum thrust is obtained when the equivalence ratio is 1.2, and the specific impulse decreases with the increase of equivalence ratio. The change trend of thrust and specific impulse is opposite. The last part is the conclusions of this study. To sum up the results, we have the following conclusions. Firstly, the influence of equivalence ratio on RDW propagation characteristics is different. When the field is lean, the RDW height is larger, the speed loss is smaller, and the wave number is less. In the case of near stoichiometric ratio and slightly rich field, the mixing effect of the field and oxidant is the best. The detonation wave propagation velocity is the largest and the height fluctuation is the smallest. The thrust is the largest. As the equivalence ratio continues to increase, the high frequency instability of RDW becomes obvious. Secondly, an increase in RDW height means a decrease in velocity and vice versa. Last but not least, the propagation characteristics of RDW are related to factors such as mixing, combustion reaction, field type, flow conditions, detonation wave and wall interactions involving complex physical and chemical mechanisms. That's all the contents of my report. Thank you for your listening and attention, and sincerely welcome your criticism and correction.